So welcome back everyone. So this video is dedicated for grade 9 advanced students that will be discussing the first chapter of physics called Physics Toolkit and only focusing on the first section. Alright, so here we go with our first slide. So have you ever wondered, for example, let's say big questions, for example, why sky is blue, or how computer works, or how planets float in the universe. So all of these questions are part of science and specifically about physics. Why? Because physics by definition is a branch of science that involves the study of what? Of the energy, okay, of the energy and matter and how they are connected or related to each other. So we can talk about physics from small atoms, as you see here, from very small atoms to the largest galaxies. So, and all will be included into physics. Why? Because physics is about studying the nature and the phenomena around us. All right, okay, so, but before being scientists, we have to learn, first step, how scientists think. That's what we call by the scientific method. So you have this in your book, the scientific method, starting with stating the problem at the beginning. So that's the first step. Then we gather information about the problem. Then we form the hypothesis. Then we test the hypothesis itself. Then we analyze the data, and then at the end we draw the conclusion. If the conclusion is not working, then we go back to the beginning, and the cycle continues until we find a solution or a conclusion to the problem that we have. So I will walk you through this scientific method, taking into example the problem that affected us all, which is the problem of the COVID-19. All right, so let's continue with the next slide. First, here we have to state the problem. So, in the late 2019, doctors and scientists noticed something weird. Let's erase this. That people are affected by a virus, a deadly virus, that's causing a severe breath problems. They don't know at the time what was that. So that was the main problem at the beginning. So scientists, for example here, they pose questions at the beginning. They are seeing, they are observing, we have a problem. So for example here, why objects fall to earth, or what is causing day and night, or how electricity is generated. So all of these big questions or big problems that we need to find solution for. All right. So then, as the next step, scientists start to gather information. They start to learn about the problem. In the case of COVID-19, doctors start to learn about previous viruses, how they spread, how they affect the human being. So it's about already means in the past. So they start to learn what they already know about the problem itself before discovering it. So here is the second step, as to gather information or to learn more about the problem. All right, moving on. Here we have to test a hypothesis, or they form a hypothesis. So that's a hypothesis, means it's an educated guess about what might be a solution for the problem. So here on this step, doctors they propose the lockdown, if you remember. That's because they think that this virus is spreading around people because of physical touch, or by communicating between the people. So they start recommending people to wear masks or being locked down, if you remember. So that's a test, or testing a hypothesis at the time. All right, so that's our fourth step of the scientific method. And then as well, in the next step, we have to analyze the data. Okay, so they gather information, they test the hypothesis, and even they start recommending people to take PCR tests, if you remember. Millions of people around the world, they start to go to hospitals to take blood tests, or if you remember, they do PCR in their nose. So there is large and big data. All right, so how to read all this data or all this information? We have to represent it in a way that we can see it and read it. So that's where this step comes for. So we have to analyze the data and organizing the data, or here organizing the data in an easy to read table or graphs. Here we have the pie chart. This is the pie chart here. It's a circle that divided into percentage, or we have the bar graph. As you see here, we have different bars that describing the situation. Okay, so this is the step of analyzing the data. Yes. And on the last step, we have to draw a conclusion. Doctors, they decide to develop a vaccine and recommend everyone to take it as a conclusion or as a solution to this problem. All right, so based on the analysis of the data, the next step is to decide whether the hypothesis is supported or not, whether the lockdown worked, or the masks work, or even here the vaccine worked. Okay, so if the vaccine didn't work at the time, so then we have to go back to the main or the original step, which is stating the problem or stating another problem that lead us to the conclusion. So this is in a quick way the scientific method that scientists follow to solve any kind. We have millions of problems waiting us to solve. I just here took the example of the COVID-19 just to show you the steps, but you can apply this to millions of problems around us. All right, moving on. On the next part of this chapter is about peer review. So for example, when finding a conclusion or finding a solution to a problem, we have to share it with others. That's what we mean by peer review. Share it with the community. It's about the community. So what I find as a conclusion, I should not keep it to myself. Imagine a laboratory or a hospital or a doctor find a solution for the vaccine for COVID-19 and didn't share it with the world. That will be a big problem. And that's what we mean by a peer review. Means we have to show it and ask other opinion as well. Asking opinion from other doctors or other scientists just to approve what I found. Yeah. On another step, we have to being objective, and I think this is the most important part, to be objective. For example, imagine a laboratory or a doctor who find a vaccine for the COVID-19 and claiming that he is that 20% of the people taking this vaccine get cured. Okay, just 20%. That's what about being objective. If I don't want to be objective, I claim not 20%, I say, for example, in a wrong way, I say to my peer that it's not 20%, I exaggerated. I say, for example, my vaccine cured like say 50% or 100%. That's a strong claim. 100% of people took the vaccine get cured, which is wrong. Okay, that's about being objective. I have to say the truth anyway. I have to say the true value anyway, whether 10%, 20%, 5%. I don't exaggerate the result that I find, and that's what about, or what about being objective about my result or about my finding. We continue. This is the third part of our chapter, or I mean for this section, is about models. So, for example, remember at the beginning of the lesson, we just said, for example, planets floating on, in the universe, or for example, day and night. So these are big questions, but we cannot experiment it in our hands. We have to create something similar to it, and that's what we mean by a model. As you see here in this picture, there is this is a small model of, guess what, of the solar system. Here we have the sun in the middle, and we have the planets all around it. So this is a small and a quick model made by a student on the solar system. So by definition, a model is a represent, and by the way, in physics we like a lot creating models because it helps us understand the reality. Okay, for example, here by definition, a model is a representation of an idea. Okay, it's just an idea, event, structure, or object that helps people better understand. Okay, so from this model, from this solar model here, I can understand that planets are floating around the sun. But of course, it's not 100% model because the distance is not well proportioned. Okay, so model, keep it simple. Model, it's just a simple representation of a phenomena or an example or a problem that I'm seeking a solution for. Here is another model, but from the world of engineering. Or if you know that pilots don't go all the way and drive the plane. Okay, so they have to go into simulation or a model. That's what they mean by a model. So if they pass the test of driving an airplane through this model, then they will be ready to drive the real airplane. So you see, models are everywhere. Okay, in schools, in airplane, in describing, as you see before, the solar system, or even when describing the atoms. Okay, because atoms are too small, we cannot see it by ourselves. We have to create a model that represent this tiny thing, which is the atom. So, and models, by the way, they develop through the years. So, for example, take here a model by Thomson in 1904. This is a very old model about the atom. He's stating that all of this is the positive charge, and here the negative charge, the balls, are representing the electrons. Okay, it was a very primitive model, but it was advanced at the time. Then we have Rutherford, another model in 1911. He stated that we have a nucleus in the middle. We have a nucleus in the middle, and the electrons are all around. Okay, he positioned the electrons all around the nucleus. And then we have what do we call, by the latest model that we're still working on it now, right now, which is the cloud model, electron cloud model. Why cloud? Because on opposite or in contrast to what Rutherford said, that in the cloud model we cannot pinpoint or we cannot state where the electrons are around the atom. We don't know. So that's why we say it's a cloud. We don't know the position of the atom right now or right here. It's very difficult to define the position of the atom. So that's why we say it's about a cloud of electrons. So that's the latest model of atom that we developed so far. All right. Yes, we continue. So, I think this is the last part of this section, defining the difference between theory and law. So, by definition, a scientific theory is an explanation of things or events based on knowledge gained from many observations and investigations. All right, so this is what we call by a theory. Theory, like models also. Theories develop through the years. So for example, we have old theory, we have modern theory, we have current theory. Theories are developing through the years. You can name, for example, the Big Bang theory, or let's say the parallel universe theory. We have millions of theories. Okay, they try to explain one law. So for example, I have 1, 2, 3, 4 theories trying to explain only one thing, one law. So we have multiple theories. So all of these, let's say, are theories trying to explain only one law. Theories with an S and underline S. we have multiple theories trying to explain only one law. We have a beautiful example here in our book, an example of, I don't know if you can see it clearly here. We have the example of the theory of, or the law of gravity. We have 4 theories as you see here. So this is theory number 1, as you see here, by Greek or by Aristotle, trying to explain the gravity, the law of gravity. Then, or let's talk about the first point first. So in the Greek, or in the old times, the Greek philosophers, or I mean here Aristotle, trying to explain the law of gravity. Okay, law of gravity. So he's stating that all objects fall to earth. Why? So let's take this ball here. All objects fall down or fall to the earth because they want to join their mother earth. They want to join their nature, their origin. So that's why they fall down, they don't go up, because they want to join their original nature. Okay, so that was the first idea. It's a very old idea about, and this is a theory, by the way. This is the first theory trying to explain the law of gravity. Then we have another theory developed by Galileo, another genius as well. In the they didn't mention the year, but Galileo is very made an important observation or experiment at the time. He take 2 objects. One is very heavy, the other one is so light, and he find out, and also of course he's trying to explain the law of gravity in his way. So one object is so heavy, the other one is so light. He find out that both of the objects, when released, both of them hit the earth on the same time, no matter their mass. Okay, no matter how heavy or light they are, both of them will hit the ground on the same time. That was his explanation, or his theory trying to explain the law of gravity. Then we have Newton, another genius as well. He also trying to explain the law of gravity, but this time using the very important word. He said it's about force of attraction. He included a new word to the law, or to his theory. He said that law of gravity is because of force of attraction. Attraction between the heavy body, which is the earth, and the small bodies like me, the ball, the car. Okay, he included the force of, as you see here, the force of attraction, and that was revolutionary at the time. He's trying to explain the law of gravity using his theory. And then we have, of course, the latest, and this is the most modern theory by Einstein, and of course, which is also the most difficult one to understand. He is trying also to understand or to explain the law of gravity using the space and time reference. It's so sophisticated and so developed theory, using his general theory about relativity, trying to explain again the law of gravity using the space and time. This is not our topic for today, maybe for later on, but just to show you, we have multiple theories, 1, 2, 3, and 4 theories, trying to explain only one law, which is the law of gravity. Yeah, we continue. Okay, here we come with the questions. Okay, so first one, summarize the steps you might use to carry out an investigation using the scientific methods. So all scientific methods use the pattern that I showed you at the beginning. First of all, we state the problem. So this is stating the problem. State the problem. Then we gather information about the problem. We gather information about the problem from the already written books, or we ask other scientists or other doctors about the problem. Then we form or test a hypothesis. We form a hypothesis, which is an educated guess, and this is very important step of the scientific method. We form a hypothesis, we test the hypothesis, we analyze the data, okay, or we can make a small drawing or represent it in a better way. For example, I show you the pie graph or the bar chart, okay, and then at the end we draw a conclusion. Again, if the conclusion we are not satisfied with the conclusion, we didn't find a solution, then we have to go back again and again to the first step of stating the problem. All right, so that was for the first question. Okay, so second question, define the term hypothesis and identify 3 ways in which a hypothesis can be tested. So, by definition, a hypothesis or term hypothesis is about an educated guess of what might be the solution of the problem that I faced at the beginning. It's an educated guess. It's not like guessing. It's a guess or a answer based on what I learned from the information that I gathered. Okay, so 3 ways in which a hypothesis can be tested. For example, you can say doing a model that I showed you, okay? So a model that helps us understand the problem or a phenomena from a better perspective, creating a model. Or on the second step, so first have a model, second step, do an experiment. Okay, so if you go back to the example of the COVID-19 that I gave to you, so doctors propose to do an experiment, so asking people to wear masks, so just to stop the flow of the virus, or doing a lockdown sometimes. So this is also an experiment. Okay, so this is about warning people or telling people to wear masks to stop the contamination. Okay. Also, the third step is to have an observation. So for the third step here identify 3 ways in which a hypothesis can be tested, which is the observation. So, for example, going back to the example of the COVID, so observation here in this case, so we observe that most important that elderly people who are aged, for example, in their 70s or in their 80s, are the most vulnerable people affected by the COVID-19 and sometimes causing death for them. So this is on a simple observation of the problem that we faced. Next question. Here we have, describe why it's important for scientists to avoid bias. Bias means, as I showed you before, exaggerating the results I found. For example, if you remember, if I found a cure that helped 20% of people, I don't exaggerate the result showing that it's 50% or sometimes 100%. That's a bias, which is a mistake, okay, which is wrong. Okay, so scientists have to avoid, we have to go away from the bias. Okay, going to question 4, we have to explain why scientists use models. Give an example of a scientific model not mentioned in the section. So I already gave you the example of the model of the solar system. Okay, so why scientists use models? Just to make the idea simple for the community or for themselves to represent a problem or a phenomenon. Okay, I showed you like the simulation of the engineering or sometimes the solar system model. Okay, the solar system is extremely gigantic. Okay, so we represented in a small model for us to have a glimpse of what's going on or just an idea about the solar system. Here we are with question number 5. So explain why scientists or scientific theory cannot become a scientific law. So as I showed you, so because the theories develop through time, as you see in the example of the atoms, the theories, not in the atom, I mean the theory about the gravity. We have 4 sages, from the Greek to Galileo to Newton to Einstein. So this developed through the time, trying to explain the law of gravity. Okay, maybe because the developing in the instrument they are measuring the gravity, or doing more calculus, more advanced calculus, trying to find out a solution for the problem. So that's why theories are developed through time, from time to time, trying to understand a single law. In this example was the law of gravity, but we have multiple laws. Now with question 6. So here they are saying that analyze okay, so your friend conducts a survey asking students in your school about lunches provided by the cafeteria. She finds that 90% of students, 90%, let's underline this is very important, 90% okay, of students surveyed like pizza. Okay, she concludes that the scientifically proves that everyone like pizza. Everyone, let's underline this again also. Everyone, or a little bit higher. Okay, how would you respond to her conclusion? So a girl doing a survey in her school find out that 90% of students like pizza, and then in her conclusion she said that everyone like pizza, which is there is something wrong here. Okay, so she find that 90% like pizza, yeah, but she is stating that all of them, all 100% like pizza. So there is a contradiction. There is a contradiction between what she found and what she is claiming. Okay, so how would you respond to her conclusion? I will tell her that I'm sorry but her conclusion is wrong conclusion. Okay, she could say instead that the majority like pizza. Okay, or just stating that 90% like pizza but not all. Because what about the less 10%? So 90%. What about the less 10%? They hate pizza. They don't like pizza. So that's why we cannot say all, okay, or everyone, which is wrong. Everyone stating everyone is wrong. All right, we continue with question 7. Okay, here we are with question 7. An accepted value for free fall acceleration of 9.8 meter per second square. So the acceleration here is found by scientists, which is 9.8 meter per second square. In an experiment with the pendulum, by the way, you can use pendulum to test the gravity. Okay, so you calculate that the value is 9.4. It's different. It's near it, it's close to it, but it's less than the real value. So should the accepted value, which is this one, the 9.8, the accepted value, be tossed out to accommodate your new finding? Tossed out means rejected. So should we reject 9.8 and accept 9.4? What do you think? So scientists say that the gravity is 9.8. I did an experiment and I found the gravity is 9.4. So which one should be rejected and what to do in this case? Of course, we have to keep this value, the 9.8, we have to keep it. Why? Because scientists use the scientific method to calculate the 9.8, and then of course, the most importantly, it's peer reviewed. Remember peer reviewing? When if someone finds a value, share it with the community to approve it. So this 9.8 value have been approved by the physicist or by the scientist. Okay. However, this value it's close to the real one, 9.8, but I did this experiment. It's not peer reviewed. Has not been accepted or approved by other scientists or physicists. So that's why I have to reject my value and I keep with the value already shared or already known in the community. Okay, that's it for the chapter 9, the first section. I hope you liked my way of delivery, my new way of delivering the content. And see you in the next video.